Okay, I would like to show you the application to traffic lights. I have a T junction like this, okay? And I have all possible directions for vehicles, okay? I can have this one, is this any better?
Yes.
Green? Okay. So, going like this, and I call this A. Okay? And going like this. And I call it B. Then I call C. Going C. Going like this. D. Going like this. E. Going like this. And F. Going like this, okay? And of course, we cannot have that these go all together, but also, for instance, we cannot have that, for instance, D and F go together. So what we do is to build a graph with all these A, B, C, D, E, F, and we draw the incompatibilities. So, for instance, A is incompatible with E because, okay, because they might hit together, intersect when if they go together. So A and F, and then that's all because that's the only possibility for an accident between A and anybody else, okay? Then, what about B? B with the C for the same reason. And of course, also with the D, okay? And also with E. Then C with B, okay, and with nothing else, and D with B already seen, and with E of course, with E and F, D with E, and with F, okay? E with the previous ones, F with the previous ones. So this should be the graph. Do you agree? Okay? Tell me.
A and E are similar to B and C. B and C have the same position like A and E.
Oh, yes, sorry, I had it wrong, actually. A and D, yes. F and E. That's all, I think. Okay, so what's the problem? To color with the minimum number of colors, 5. Because of course we might do the silly thing of giving one color, that means one period to each of these ways. Okay, so I first let go A, then I let go B, and so on. But it's a silly way of doing. So we are looking for maximal independent sets. For instance, possibility is E, F, and C. Okay, I give period color, and so period 1 to E, F, and C. Okay, and then give period to B and A, and period 3 to D, for instance. That's a possibility. But any other coloring with the 3 will give us the minimum possible number of periods into which to divide time. Thank you for your correction. Okay? And that again, whenever you have some sort of incompatibility, you can build a graph with vertices of the relevant situations and adjust the incompatibilities, and then searching for the minimum number of colors for a proper coloring will give us the optimal solution. Okay. Here you might also think of other, of course, for choosing, since you have different colorations, different colorings with 3 colors, you might have other, you are engineers, so other criteria for deciding one coloring instead of the other. For instance, it might be that you try to move vehicles more or less in the same amount at each period, okay? Okay, anyway, minimum you need 3 periods for making all these vehicles go without interference. Okay? All right, now let's go to planar graphs. Why do I say that this and the next chapter are culturally important? Because, well, the last chapter we do, which is directed graphs, is necessary. Why? Because we have so far only considered symmetric situations, symmetric relations, unordered graphs in which if vertex A is connected to vertex B by an X, the same thing is, the same relation is from B to A. It's unordered, okay? But quite a lot of situations are not symmetric, and so the correct way of describing, if you want to describe binary relations, meaning which in a sense consider 2 objects at a time, graphs are wonderful, but they must be directed in the sense that you need to have a first and a second vertex in your edge, which will be called arc. Okay, so it's Of course, directed graphs are a necessary complement to what we have done so far. This chapter, planar graphs, is important also for applications, but also because it gives us the connection to a broader part of mathematics, which is called topology, and which relates graphs, which are, for the moment, just, if you want, we have seen them just as combinatorial structures, algebraic structure, if you want to say so, okay? But if you realize them, you can always realize a graph by points and arcs or curves. We always draw them on the plane, maybe with intersections which are not meant to be vertices, okay? You can always do a geometric realization of a graph in three-dimensional space anyway. They are, if you want to consider them geometrically, they are one-dimensional objects, okay? And so planar graphs, and the chapter is focused on the plane and on the two-dimensional sphere, okay? The spherical surface, which in mathematics is called the sphere. What generally is called the sphere in mathematics is called the ball. Okay, so the full thing is the ball, and its surface is the sphere. Okay, so I'll always use this term, sphere, for meaning spherical surface. All right. So here the focus is on plane and sphere, and we'll immediately see that they are very much connected for what concerns embedding a graph into them. But also with the general idea of embedding a graph into a surface, and so looking at properties of surfaces, and this is the start of a big important part of geometry, let's say, which is topology and geometric topology in particular. Anyway, we had already seen this problem of being able or not being able to represent a graph in a plane without any crossings, which are not the vertices themselves, okay? And so we have already called planar a graph, meaning a combinatorial structure, set of vertices, set of edges, incidence function. Planar if there exists a geometric realization in the plane where you have no intersection in the inner points of the curve arcs which represent the edges. Okay? So, what can we say about them? Can we find a rule for a graph to be planar or not? And there are quite a lot of interesting things to say about this idea of embedding into the plane. So, a graph is said to be embeddable in the plane or planar if it can be drawn in the plane so that its edges intersect only at their ends. Such a drawing is called a planar embedding of G. A planar embedding of G can itself be regarded as a graph isomorphic to G, in the sense that those points will be the vertices, those curve arcs will be the edges, and if you have that your graph is actually something like the chemicals we were talking about, and so then you have a combinatorial, very abstract graph, which is isomorphic to the one which you are drawing. Okay? And of course, planarity is very important in printed circuits, okay? Because you have a complicated circuit, you want to know whether it's possible to make a board with it, and so you need to know whether the graph that you have is planar or not, and maybe how far you are from planarity, okay? So how many bridges you need to put on your board, for instance. Okay, A planar embedding or a planar graph is a plane graph. So mind the difference between planar and plane. Plane is the graph already embedded into the plane, and planar is maybe an abstract object which is isomorphic to a plane graph. For instance, this is a planar graph, meaning that you can draw it without these intersections easily by putting this arc this way, this edge this way instead of this. Okay, but the graph itself has vertices which are not points, are these directions of the vehicles. All right, and that abstract graph is isomorphic to a certain plane graph, which we can draw. Okay, I will not use Jordan curves in the proofs, but still let me mention this because it was a sort of a surprise more or less 1 century ago, a little bit more, that it was not immediate to prove something which is very intuitive, which is this. Take a continuous non-self-intersecting curve whose origin and terminus coincide. Okay, so a curve in the plane starting and ending at the same point without any other self-intersections other than origin and end. Okay, drawn in a plane. Okay, then you if you take away the points of the curve, Jordan's theorem says that you are left with the two pieces of the plane, which are disjoint. One is bounded, the other is not bounded. Okay, and if you in the original setting, so with the curve on it, if you take a point inside one of the region and the point inside the other region, then any curve connecting the 2 points must intersect the curve we were talking about. The idea is so intuitive that it seems a stupid thing, and actually it was strange for the first topologists to realize that you needed a proof, and it's not an easy proof, absolutely not. So if you take a curve, C, no name, okay, a curve C, and then in the plane you take it away, a Jordan curve, closed and non-self-intersecting, you take it away, you're left with two pieces, one is bounded, one is unbounded, and if you pick up any point of the first region, any point of the second region, then if you want to join them with the arc of a curve, that arc intersects the original curve in at least one point, which is absolutely intuitive, but it's not trivial at all to prove with the techniques they had 1 century ago. Later on, algebraic topology was invented and things became more simple. But when you have a very massive theory, so it's simple in a big theory, or it's difficult in an elementary theory. Okay. All right. Interior and exterior. You can use that for showing that K5, do you remember K5, the complete graph with 5 vertices in non-planar? And also that K33 is non-planar. We'll use another way for proving these two, non-planarity of these two. You can also think of embedding a graph into a different surface than the plane, okay? And they correctly put you here the definition of surface and actually of manifold. A two-dimensional manifold. What is a k-dimensional manifold is something interesting, and if you are dealing with robotics in particular, in general, with configuration spaces, then you need to know more or less what an n-dimensional manifold is. It is a topological space, so somewhere a space where you have the notion of open set, essentially, and of neighborhoods and continuity for maps, in which you have that for each point you have a neighborhood of that point which is made exactly like a piece of Euclidean space of dimension n. So what is a surface, meaning in a two-dimensional manifold? A topological space where for each point you have that there is a neighborhood which is, the correct adjective is homeomorphic, meaning that you have a continuous function with continuous inverse from that neighborhood to a neighborhood of a point in the plane. Okay? More or less the idea is this. If I take a torus, for instance, then for each point I have a neighborhood in the surface, okay, which is homeomorphic with a certain neighborhood of a point in R2. This is our torus T, and for each point you have this thing. You have this map, which is continuous and has a continuous inverse. Maps like this are called homeomorphisms, and so a n-dimensional manifold is a space where which is locally Euclidean, but globally not. Okay. You can see very well that this is not the plane, okay? You have here some loops which cannot be contracted to nothing, okay? Whereas in the plane, all loops can be contracted to nothing, for instance. This is a way of discovering that you don't have a global homeomorphism between the torus and the plane, or the torus and the sphere. Not a complete continuous map from torus to a plane, and from plane which has a continuous inverse from plane to torus. It's not possible. They are not topologically the same thing, but locally, yes. Okay? And since practically all regular configuration spaces are in this situation, they are not globally Euclidean spaces, but locally they are like Euclidean spaces. The study of these spaces and manifolds is very important for mathematical physics, mechanics, and so on. Okay? But for the moment, let's just think of two-dimensional manifolds, so objects which are locally like the Euclidean plane. Okay, I won't mention orientability and non-orientability, but you might anyway know something about the peculiar thing which is the Möbius strip. And anyway, you have that you can embed K5 on the torus and you can embed K33 on the Möbius band. Okay? So graphs which are not embeddable in the plane can be embedded in more complicated surfaces. for a graph to be embeddable into the plane or on the sphere is the same thing. Why? Because between plane and sphere we have this nice thing which is called stereographic projection. Okay, you place the sphere on a plane so that it touches in the south pole of the sphere, so to say, and now from north pole draw all possible half lines, okay, straight half lines, okay, each of them intersects in exactly one point the sphere and in exactly one point the plane. All right, these points are put in where you have a map sending so each point of the sphere apart from the north pole to each point of the plane. So it's a bijection between sphere minus one point and the plane, and I can assure you that it is continuous and its inverse is also continuous, so a homeomorphism. Okay, and so if you take that point away, you have this complete correspondence. And also, I've never showed you the Wolfram demos because there are not quite a lot for our course, unfortunately, but you can see a bit how this projection works, okay, by seeing such things. And if you want, you can do it with a square, and other things. Okay. Just to see what happens if you project something which is on the sphere, you project it on the plane through this, which is called, as I told you, stereographic projection. So if you have a graph which is embedded in the plane, you use the inverse of the stereographic projection and you go to the sphere. On the contrary, if you have a graph on the sphere but not having any point in the North Pole, then you can get an embedding on the plane by using the stereographic projection. Okay, but of course, if your graph goes through the North Pole, you can just move the sphere slightly so that the North Pole is not a vertex, not an edge of the embedded graph, and so every graph which is embedded in the sphere is also can also be embedded in the plane and conversely. All right. And so you have this theorem: a graph is embedded in the sphere if and only if it is embeddable in the plane. Okay? You can try, and I suggest you do, to embed K5 minus an edge, any edge, and also you can embed K33 minus any edge. All right? By the way, this thing of K5 and K33, I think is very much educational. You are not going to be teachers. Generally, an engineer has other tasks for his or her life. But I think that this is a very interesting thing for making a young person understand the meaning of a theorem. I mean, Euclidean geometry is wonderful, but it's so rigid that you can think, okay, it's rather obvious that some rules come out, okay? You have a perfect circle, then the angle at the circumference is half the angle at the center, or such things, okay, but it's so rigid that you can understand that things come out of it. But topology is very, very free, and so you have this, and I think it's a very good thing for a young person, say 12 years old, or the beginning of high school, and to say, well, you have K3, so you have A, B, and C, 1, 2, and 3, and you have to connect each of these to each of those. Do I need to make straight lines? Absolutely not. You can make any curve you want, but just they don't have to. They have not to intersect in the middle. Okay, and so you are very free, much freer than in geometry. And so you can do this, this, and this, but then you can also go around, and and then you can go this way, and so on and so forth. And so you are very free, and you think that you might find a solution of connecting all to all, and you try and you try and you try. After a while, the young person will say, okay, I can't find any. But now it might be possible to understand that there is a difference between not finding any and it is impossible. Do you see what I mean? So I think that the meaning of a theorem is conveyed much better in such a situation than in the rigid geometry, If I tell you, well, it will never be possible, whatever you do, go around, make any term, do whatever you want, but you'll never be able to solve this, and it is also possible to prove it, then the young person might understand rather well the meaning of a theorem saying it is not possible. And when we talk in a few minutes about the Euler characteristic, it will be also very interesting, in my opinion, for a young person. But you are not so young, Dual graphs. Assume that we have a plane graph, So now we are going to build what is called the dual graph, in which vertices will not be the original vertices, but other things. Let's see. A plane graph partitions the rest of the plane. If you take away the graph from the plane, you are left with pieces of plane, a number of connected regions, meaning the region that connected pieces, of plane. These are all open sets in the plane. You close each of these regions by itself, and you get what are called the faces of the graph, And for instance, here you have these faces, which are one which is unbounded out, so to say, of the graph, and then some other. Here there is one which touches itself through this edge E11, for instance, Others which touch one another, So we use capital F of G as the set of faces, and phi of G, its cardinality, so the number of faces of the plane graph. Each plane graph has exactly one unbounded face that comes from as a corollary from Jordan's curve theorem, which is called the exterior face, F1 in the example. Now, if you pick up a vertex V of a planar graph, then G can be embedded in a plane in such a way that V is on the exterior face of the embedding. How can you do that? Think that you have a vertex which is which is not on the exterior face. Say something like this. Okay, so this vertex is not on the exterior face. The exterior face is this one, all right? But how can you do so that it becomes the vertex? Let's complete it like this so it will be easier to recognize it, okay? A, B, C, D, E. So what can I do? I can assume that this is the projection of something which is drawn on the sphere, okay? Here, like this, for instance. With the North Pole here, and so you have the projection which goes like this, okay? Now what can we do? We can, what is the correspondent thing of the unbounded, the exterior face in the sphere? It is that part of the sphere which contains the North Pole, the projection pole, okay? So now what can we do? We can just move the sphere so that the North Pole is inside. Okay, and then if you project again, now your the exterior region will be this one, and the vertex A will be in the exterior, on the exterior region. Okay. Now, the boundary of a face of a plane graph is denoted by B of F, F being the face. If G is connected, then B of F can be regarded as a closed walk in which each cut edge is traversed twice, okay? We can see it here, for instance. Here we have a region F5, and so you can do a walk like this: E8, E11, E12, again E11, E10, E9, and then you are back to the initial vertex V6, okay? And actually, since this is a cut edge, you have gone through that edge twice, all right? Same thing happens here. If you take the exterior face, then you can, for instance, do from V6, E7, E6, E5, E2, E1, E6 again, E10, E9, okay. And when B of F contains no cut edges, it is actually a cycle, okay? And each vertex will be met, of the face, will be met just once. And you can see these boundaries, see them in the graph, in the plane graph above. A face F is said to be incident with the vertices and edges in its boundary. If E is a cut edge in the plane graph, just one face is incident with E, on both sides, so to say, okay? That's for reserved to cut edges. Otherwise, for a link, which is not a cut edge, you have two faces incident to the same edge. An edge separates the face incident with it. That's what we generally say. The degree of a face is the number of edges with which it is incident, but counting each cut edge twice, because we need it twice when going around the boundary. Okay? So that's the number. It's a bit like the degree of a vertex when you have a loop, but the two things are actually very much connected. And so the degree of a face, all right? And you can see examples here, but I'm not going through it. Okay. Now you can define another graph G star as follows. You pick up a vertex which you call F star for each face F of the original graph G, and corresponding to each edge E, there is an edge E star of G star. Two vertices F star and G star, which correspond to two faces F and G in the plane graph, are joined by an edge E star if and only if the corresponding faces F and G are separated by the edge E in G. Okay? And so, for instance, if you have a cut edge and you have a certain face is confining with itself, then actually you'll have a loop in the graph G star. G star is called the dual of G. And the plane graph and its dual are shown here. Here you have the most natural thing is to superimpose one to the other. But if we take just the abstract notion as it was introduced by the book, you pick up face F1, and then you draw a certain vertex F1 star. Then you pick up a face F2. Then you draw a certain vertex F2 star, and so on and so forth. And then you follow all the indications. F1 is adjacent to itself through edge E8. And so F1 star is adjacent to itself through an edge E8 star. Okay? And you draw all that. But the nicest thing is to put a vertex of the dual inside the region it represents, and an edge of the dual to cross the corresponding edge in the original graph. Okay? And so you have up to isomorphism that the thickened edges here are the ones of the dual graph of the original plane graph, drawn on the plane with this idea. And it's exactly what I told you already as the first idea which they had for trying to solve the four-color problem. Meaning, you have that map with all the regions. Okay, an idea is put a vertex at each capital town of each of the region. Okay, and put an edge between two capital towns of regions which have a common part of the boundary. Okay, and so you can draw on the same map. You can draw this, which is called the dual graph. And then coloring the regions becomes coloring the vertices of the dual graph. Okay? Now we'll play with so to say, I don't see you very enthusiastic of this type of game, but anyway, you have to digest it, and first I give you 15 minutes break.